Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection, as usual. Today, actually, not really a theorem, or because there is just no way to choose any nice theorem about the Chebyshev polynomials because there are too many nice theorems about Chebyshev polynomials. So I would rather explain what Chebyshev polynomials are from my biased point of view and pick out kind of my favorite jewels among the many theorems about Chebyshev polynomials. So the Wikipedia page on Chebyshev polynomials is one of the longest I've ever seen. It's really amazing. So those polynomials, I try to explain that they kind of generalize Fibonacci numbers, and Fibonacci numbers, of course, appear everywhere in mathematics. So Chebyshev polynomials are also everywhere, literally, in mathematics. They're not quite Fibonacci numbers, as I will explain them, or as I will introduce them. There will be more like Fibonacci numbers with some signs involved. So signs are extremely crucial, and in some sense, in the end, the signs make everything work, and the Chebyshev polynomials are, again, in some sense, more important than the Fibonacci numbers, which is a really strong statement, right? Being more important than the Fibonacci numbers. But let's go on and start such that we are all on the same page. Let me recall the Fibonacci numbers for you. Of course, all of you have seen them, so they are here. So they are given by this rule that you choose some starting condition, and then 2 is the sum of the two previous ones. 3 is the sum of the two previous ones, so 2 plus 1 in this case, so they're given inductively. 5 is the sum of the two previous ones, and so on. Right, so 34 is the sum of the two previous ones. It's 21 plus 30. Okay, Fibonacci numbers, pretty old, going back to a very famous book by Leonardo de Pisa, linked in the description. And they're just everywhere, right? Everyone knows them, related to the rabbit problem, which actually I think was the original problem in the aforementioned book. But anyway, so they're really cute. They appear everywhere. In particular, they're in Pascal's triangle in the following way. So here's Pascal's triangle, as you can see. So just the usual Pascal's triangle, where each entry is basically a binomial coefficient, or basically it is a binomial coefficient. And the way to obtain the Chebyshev, the Fibonacci polynomials or the Fibonacci numbers is to cut in this illustration from northeast to southwest and add all numbers. So 1 adds to 1, 1 adds to 1, 1, 1 adds to 2, 2, 1 adds to 3, 1, 3, 1 adds to 5, and so on. So 3, 4, 1 adds up to 8, and so on. We have a very cute relationship between Fibonacci numbers, Pascal's triangle. Pascal's triangle, of course, extremely important in mathematics and ancient and well-known, like Fibonacci numbers. So the generalization of Fibonacci numbers are maybe Fibonacci polynomials, and it's just a really easy idea, strikingly easy, so life-changing easy if you want. No idea really is life-changing easy, but anyway, so it's really nice. So it takes a recursion of the Fibonacci numbers, which I just explained. So 5 was the sum of the two ones before. So Fn is the sum of Fn minus 1 and Fn minus 2. Take the same recursion, throw in a variable, call it x, and you get the Fibonacci polynomials, right? So you fix some starting conditions, whatever. So secretly, here's also the starting condition 0 if you want. I'm doing exactly the same thing. I'm defining a polynomial in a variable x, choosing two starting conditions, whatever, and then this recursion and this only extra term, which is different, which is really a generalization now of the Fibonacci numbers, is that I throw in this x times Fn minus 1 here. And by definition, if you evaluate this polynomial at 1, you get the Fibonacci numbers. But this kind of a finer version of the Fibonacci numbers in the following way. So the Fibonacci numbers, so this 89, 98 here is just the sum over all the things that you see in this northeast to southwest slice. And for the Fibonacci polynomial, it's the coefficients that you see here are the corresponding coefficients appearing in the Fibonacci polynomial. Okay, so the leading term has coefficient 1. It's an x to the whatever, how many Fibonacci numbers you see, and then you go down in steps 2. So yeah, so let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I guess I might be off by 1 here, but it doesn't really matter. I guess the first one here is x to the n, and then it's 9x to the n minus, so x to the 10 here, and then it's 9x to the 8, and then it's 28x to the 6, and so on, right? So you just go along and pick up the coefficients. As I said, up to a plus minus 1 error here in my exponent, that's what you do. You always jump down by 2, and you take the coefficients that you see in the Pascal's triangle. And of course, as I said, this generalizes Fibonacci numbers by just specializing x to 1. Pretty nice idea. Generalize Fibonacci numbers by throwing an extra variable and do exactly the same recursion. Fantastic. Enter the Chebyshev polynomials. Same picture, really just the same picture. It has one crucial difference. I take the same recursion, but in the middle, I put in the minus sign. Really the same. So it works in exactly the same way. So you take Pascal's triangle again, and well, you throw in a sign at each second, whatever. In this case, it is, again, it's a northeast to southwest slice. In every second one, you throw in a sign. And that's it. And now the coefficients of the corresponding Chebyshev polynomials are given as exactly the same slices. So here 1, 9, 28, 35, 15. So 1, 9, 28, 35, 15, 1. And that's the corresponding Chebyshev polynomial. It's the same as a Fibonacci polynomial up to a sign that is somewhere built into the definition. Right, so I say it again, there are Chebyshev Fibonacci polynomials, generalizing Fibonacci numbers by very smartly putting in a variable x, such that if you specialize x to 1, you actually do get the Fibonacci numbers back. I do exactly the same thing. I just throw in the sign at the right spot. So namely here in my recursion, and I get the Chebyshev polynomials. Strictly speaking, they're called the Chebyshev polynomials of the second kind. And strictly speaking, I've normalized them. When compared to the Wikipedia definition, I link the corresponding normalization in the description. It's pretty harmless. But in this way, they fit much better to the story about Fibonacci numbers. And really, it's really the same. So in some sense, it's really the same because you just have the coefficients are given by signed Pascal's triangle in the way I explained. Well, in contrast to the Fibonacci polynomials, which are given by Pascal's triangle. And you also can, in a very funny way, you can get back the Fibonacci numbers by specializing x to I, not to 1, up to an overall correction term that you just multiply. But you can ignore the correction term. So Fibonacci polynomials, we cover Fibonacci numbers specializing x to 1. Chebyshev polynomials, still a generalization of the Fibonacci numbers, but now you have to specialize x to I. Very good. So at this stage, it looks like I have done nothing really interesting, accepting already that I already know the Fibonacci polynomials, which really is a crucial step, right? Going from the numbers to the polynomials is not completely obvious. As soon as you have the polynomials, it's obvious, of course, how to go back, just specializing x to 1. But the first step was not really easy or not really obvious. In hindsight, it's, of course, really easy. And now I just throw in a sign, and I tell you the Chebyshev polynomials are more important than the Fibonacci polynomials. So that's kind of my idea here, or the story of this video. So I'm trying to convince you right now, in the next few minutes, that these Chebyshev polynomials are actually better than the Fibonacci polynomials, and therefore they're also somehow better than the Fibonacci numbers, which is a really strong statement. You should take everything with a grain of salt, of course. I mean, what does it mean to be better than the Fibonacci numbers, right? Anyway, so this is a setup. So Chebyshev polynomials defined by Pascal's triangle by sine Pascal's triangle. Turns out that the sign is extremely crucial in the following sense. So if you take the Fibonacci polynomials, then by definition, if you look at the triangle, there are no negative numbers. So they're all kind of this form. So it's some power of x times some natural number times power, so a positive number times the power of x plus a positive number times the power of x plus a positive number times the power of x. So they don't have so many exciting roots. So I've just plotted the first few Fibonacci polynomials up here, and they don't have very exciting roots. That's just what it is. By definition, they only have positive coefficients appearing, and so you shouldn't expect that they have really nice roots. The Chebyshev polynomials, with contrast, plotted down below here, they have really, really cute roots. And as you can see, the polynomials look pretty different, right? So the Fibonacci polynomials are more like hyperbolas, parabolas like things. The Chebyshev polynomials are more like sines and cosines. I'll show you an animation in a second. And sines and cosines have very, very important roots, of course. And it turns out that the roots of the Chebyshev polynomials are among the most important numbers in mathematics. And they are very easy to write down. They're all of this form: 2 cosine k times pi over n. So n is the n of the Chebyshev polynomial. You take the 10th or whatever, and the 10th has exactly those roots. Pretty cute, pretty cute. Let me show you an animation of the Chebyshev polynomials. So here's my animation. It will run in a second. So this plots the Chebyshev polynomial in the crucial range, which is usually -2 to up to 2. I will come back to that in a second. That's where the roots are, where all the roots of the polynomials are. And as you will see, as n increases, the Chebyshev polynomials really don't look like polynomials anymore. They look like cosines or sine functions. So let's have a look. So it starts with something like n equals 2, and then it decreases n as we go along in the video. Yeah, it looks more and more like a cosine function. So actually pretty cute. And you can guess the rest of the pattern. Now the video runs backwards, and the roots that you see here are those funny cosine numbers that I told you about, and they're extremely important, as I said. So kind of Chebyshev polynomial is kind of like what the cosine and the sine functions are for analysis. That's what the Chebyshev polynomials are for algebra, as we are going to see in a second. Okay, back to my slides. What's the difference between Fibonacci and Chebyshev polynomials? One has sines, the other one doesn't, and sines makes it much easier to see nice roots, because now we have kind of alternating coefficients, and if you have alternating coefficients, then you have really nice real roots, right? It's kind of the point here. So the Chebyshev polynomials, they kind of fluctuate between 2 and -2 all the way, while the Fibonacci polynomials, they look a little bit boring. And it turns out, so here are my favorite statements about the Chebyshev polynomials. There are zillions of statements about Chebyshev polynomials, as I said, and it's always extremely surprising where they just turn up. And it turns out that those numbers, those cosines, are super important, that they kind of turn up everywhere in mathematics. That's why I like them so much. So when I first met Chebyshev polynomials, I was just super confused. So it was in the realm of representation theory of SL2. So you see Chebyshev polynomials turning up. I will come back. I will show you. You can already see it. I will come back to that in a second. And I found that very surprising. Nowadays, I'm not surprised anymore. If you see some part of algebra, some part of mathematics, some part of life, you will see Chebyshev polynomials. It's not a big surprise anymore. Maybe because they really generalize those Fibonacci numbers. So one of my favorite statements is kind of the minimal algebraic integers are roots of Chebyshev polynomials. So it's sometimes it's a version of Kronecker theorem linked in the description. So basically the statement is, take an algebraic integer, and that's just a root of a polynomial with integer coefficients. Well, here comes the restriction, integer coefficients. And you wonder about the smallest ones, the one in the interval -2, 2. And it turns out that they're all roots of Chebyshev polynomials, which is kind of a very surprising statement. So they're all of the form cosine 2k pi over n, which is a pretty nice statement. It turns out that this is extremely crucial, that you have this little interval, -2, 2, because kind of the breaking point. As soon as you increase that and you ask for something like, what are the minimal possible integers, algebraic integers in a slightly bigger interval, you're kind of dead. It kind of explodes and it gets uncontrollable. It's kind of the border case where things are still kind of nice and you can classify solutions. In this case, you can classify the minimal algebraic integers. Another nice fact is actually that they form a basis. So you can always write of the corresponding polynomial ring. So you can always write, for example, x to the 504 in terms of Chebyshev polynomials. And the fun is this completely works over the natural numbers. So you never need fractions, you never need negative numbers. Really cute and surprising statement. So it's kind of, they form a good basis of the polynomial ring in some sense. They turn up in the representation theory of SL2 because they determine the tensor product rule in SL2. So the simple characters, the irreducible characters of SL2, they're encoded by Chebyshev polynomials. Again, really surprising and strange statement in some way. They appear in classification of root systems, Coxeter systems, integral matrices, in various applications in numerical analysis, and so on and so on. They're pretty amazing, and you shouldn't be surprised if you just see them turning up. So I was shocked when I first learned about this, and I hope you like them as well. So let me wrap up. Before I wrap up, let me just say that there are two versions of the Chebyshev polynomials. They're sometimes called the first and the second kind. I took the second kind because it fits nicer to the story about Fibonacci polynomials. There's also the first kind. So the first kind is usually denoted T. The second kind was the one I denoted U. So the U's are the second kind. So up to a normalization, I throwed in. Those were the second kind. And the first kind, there's a precise relationship between the two. It's linked in the description. Kind of if you know the first one, you know the other. But it turns out that the second kind seems to be more important in applications for number theory and algebra, what I just explained on the last slide, so kind of sketched on the last slide. While the first kind, which is really the same up to a certain substitution if you want, the first kind turns out to be more important in problems in numerical analysis, for example, in approximation theory. Again, they're everywhere, but kind of there are two cousins, very closely related cousins. One of them likes approximation more, the other one likes algebra more, but actually, if you know one, you can determine the other. Anyway, so here's a cute example of where the first kind of Chebyshev polynomials turns up, which I haven't explained. But anyway, there's also a first kind, as I said, you basically can get it from the second kind. And it's in this idea that you can approximate, so there's Weierstrass theorem, which tells you that you can approximate any reasonable function using polynomials. And you would like to do that in practice. You would like to feed that in a computer in the following way. You take your favorite function. In this case, it's this Runge function. It's a really simple function. It roughly looks like this. And you throw in some certain points. So you kind of think you measure, you have an experiment and you have just a discrete number of points with your measure points, and you kind of want to approximate the solution. And what you can do is you can use a polynomial of a certain degree and just throw it in, and you try to approximate the solution. So you try to approximate this non-polynomial using a polynomial of higher and higher degree. So it turns out that Weierstrass tells you that this is always possible, but it's not so easy to see, or it's not so nice with respect to errors. And that's called Runge's phenomena. So Runge gives this example of taking this function and taking equally spaced measure points. So these were equally spaced, which certainly isn't the case in my picture here. But anyway, so in this picture up here, the red points are the approximation points, and they're equally spaced. So they're equally distributed along the x-axis. And you would like to approximate this very harmless function here, just this bump. You want to like to approximate it with polynomial, which goes exactly through those points. That's the whole point. It turns out that this gets really crazy along the boundary. So if you, so Runge's phenomena says if you do this with a polynomial of higher and higher degree, your error explodes. So here's the error in the interpolation, which means the difference between the blue, so the blue is the approximation polynomial, and the one in the background that you can't see is the red curve, is this bump, and the difference between them, well, in the middle, as you can see, there's almost no difference between the blue curve and the red curve. So you can't even see the red curve because the blue curve is just lying on top of it. And there's almost no error in the middle, but along the boundary, it really explodes. So the difference here goes up to 600,000. It gets as big as you want. Really bad. And this is a huge problem for approximation theory. You would think that Weierstrass theorem tells you just make your degree as big as you want, and you can approximate your function using polynomials. But it crucially depends on that's kind of the point here, Runge's observation. It crucially depends on the used anchor points, the used experimental points, the spaced points you use where the polynomial should go through. So it turns out that kind of the best nodes you can use are, again, the roots of the Chebyshev polynomials, in this case of the first kind, so not quite the ones from before, but almost. So if you use those roots, and use the same strategy, approximate the function using a polynomial of the corresponding degree, which goes through all those red points. As you can see, it's almost perfect. The interpolation error is absolutely negligible. So don't get confused, because this looks very flat here and this looks very strange. The corresponding scale is also completely different. So this goes up to 600,000 and this goes up to 0.00010. It's almost nothing. So, and this has to look like this because so whenever it hits 0, this is where the polynomial and the function agree. These are my approximation points where the polynomial goes through and they're on the function. And otherwise, this is really harmless. I mean, this goes up to 0.00 whatever. And of course, if you take n to infinity, this is a perfect approximation of the curve. So takeaway message here, if you take just random points, basically, usually this idea of approximating functions by polynomials explodes and the error gets arbitrarily big. So error goes to infinity as the degree increases of your polynomial. And if you take some nice approximation points, some nice points of your where you measure your experiment, your measurement points, then actually the error goes to 0. Turns out that some of the nicest points around there are roots of Chebyshev polynomials. Again, a very striking and surprising appearance of the Chebyshev polynomials. As I said, strictly speaking, this is the first kind, not the second, but let's ignore the difference anyway. So let me wrap up. Chebyshev polynomials, generalizations of Fibonacci numbers, Fibonacci polynomials, in this funny way that you just throw in a sign. It looks extremely silly. You just throw in a sign, and now, well, you have to evaluate at I instead of at 1. Okay, so what? Turns out that the roots of these polynomials are much, much better, and the polynomials itself are extremely well behaved and turn up in various problems, very completely different problems in mathematics. And I'm pretty sure also beyond mathematics. So in mathematics, you see them in algebraic numbers theory, you see them in representation theory, you see them in Lie theory, for example, and also you see them in approximation theory, in minimalization problems. It's just everywhere. It's just crazy. I love them. Anyway, I'm starting waffling, so I hope you enjoyed the video, and I also hope to see you next time.